Well, thank you very much for your kind introduction, and thank you for the organizers for inviting me. I very much admire organizing a conference these days. It can be quite tricky, so my admiration for them. So as you heard, my name is Emilio Martinez-Paneda. I'm an assistant professor at Imperial College London, and the work that I will present today has been done in collaboration with my friends at DTU. One is Christian Jorsen and Philip Christensen, which is a student that I co-supervise with Christian Jorsen. And basically, I plan to present a model for predicting hydrogen embrittlement. And I will explain later why this model requires two key ingredients, which are phase field fracture and strain gradient plasticity. So that brings the connection to this symposium. And part of the model has been already reported in a GMPS paper last year, but we have some new results coming as well. So just to start first, what is this hydrogen embrittlement? So you may have heard about it. It's quite a hot topic these days as a result of the use of hydrogen as a new energy vector. But it is actually quite an old phenomenon. So it was reported in 1875, as you can see in the slide, by Johnson in the Proceedings of the Royal Society, where they spoke about which he writes about some remarkable and extraordinary changes in iron and steel, in the fracture toughness and the breaking strain of iron and steel in the presence of hydrogen. And you very rarely see words such as remarkable or extraordinary in scientific papers, but the effect of hydrogen in metals is indeed remarkable and extraordinary. So one of these effects is how hydrogen reduces the ductility of metals. So you can see here that you introduce hydrogen into your samples, for example, by exposing them to hydrogen gas, then you see a very drastic reduction in the breaking strain. Another important effect is the influence of hydrogen in bringing down the fracture toughness. You can see here that for a steel that has a fracture toughness of 150 megapascals square meter will fail well below 40 megapascals square meter if you introduce hydrogen into the samples. And this is for a low strength steel. But for high strength steels, the fracture toughness reduction can be of up to 90%. And this is a key point to emphasize. The susceptibility to hydrogen damage is very sensitive to the strength of the material. So you can see here reported fracture toughness versus yield strength for a given environment, a fixed amount of hydrogen. It could be typical of seawater. And you can see that for high strength steels, the fracture toughness goes below 10 megapascals a square meter, so almost like a ceramic. And this is quite an important picture because basically there are two takeaways. The first one is that hydrogen is compromising decades of metallurgical research. We have developed high performance materials, but we cannot use them. And the second one is that by using high strength alloys, we're basically seeing hydrogen assisted fractures in many applications and environments where we never seen them before. So traditionally, hydrogen embrittlement was a problem related to aggressive environments, for example, those related to offshore engineering. However, since we want to use high strength steels because they're very cost effective and solve many of our problems like fatigue, we're using them in railways, in cars, in buildings, in bridges. And as a result, we're seeing hydrogen embrittlement problems in otherwise very benign environments. You can see this is a newspaper article, and this is one of the most famous skyscrapers in London. And just the hydrogen coming from the humidity is enough to trigger those hydrogen-assisted failures. And last but not least, you probably have seen in the newspapers quite often, quite a lot of discussion about hydrogen as a future energy vector. We already have hydrogen-fueled cars, trains, and buses in the market. And you can imagine how problematic it's going to be to store and transport hydrogen to fuel all these vehicles. So at this point, you may wonder, Emilio, okay, how can it be that 150 years after that paper in the Proceedings of the Royal Society, given how technologically relevant this problem is, hydrogen-assisted failures are not only solved, but they're becoming more and more frequent? Well, one of the reasons is that it is a quite complex problem that crosses the disciplines of material science, mechanics, chemistry. We do understand the basics. We know that hydrogen atoms enter the material, they migrate relatively fast through the crystal lattice, and they accumulate in areas of high hydrostatic stress, or high volumetric strain, where there's more space for the hydrogen to accumulate. But then what happens in the fracture process zone is a bit complicated because hydrogen interacts with the material in many different ways and at multiple scales. For example, by changing the dislocation mobility, by also bringing down the bonding strength between metal atoms, and so on. So developing predictive model for hydrogen embrittlement has long been considered sort of an elusive goal. And of course, that, needless to say, has some very important consequences for for engineering practice. So just two examples here: the San Francisco Bay Bridge, where bolts failed, and the Kashagan oil rig, which the repairment costs had a cost of $3.6 billion US. So it's quite a beautiful problem in that perspective, in that it's very fundamental, but at the same time, it has very important implications on engineering practice. So we basically tried to give it a go, and I'm developing a predictive model for hydrogen embrittlement. And this model has basically three main ingredients. The first one is a strain gradient plasticity-based description of crack tip mechanics. And I will explain why this is important. The second one is, of course, you also want to get the chemistry right. So you want to model hydrogen diffusion and ingress and couple this with the deformation problem. And then finally, we want to develop a multiphysics model that can deliver predictions. So we use phase-in fracture for that. And at the same time, we need to couple all these ingredients of this deformation-diffusion fracture problem. So we draw a mechanistic rationale to develop this coupling. I will elaborate a bit more. So yeah, let me elaborate a bit more on each of these ingredients. I will start with the first one, with this strain gradient plasticity description. And I think that's in every problem that you look at, of course, you always need to think of what are the critical variables of your problem. In this case, stresses, crack tip stresses, and hydrogen concentration. And also, what is the critical distance? And in this case, the critical distance for fracture is a few microns ahead of your crack tip, so very close to the crack tip. And there's a lot of evidence about it, but one sort of evidence that you can understand is by looking at experiments. So if you plot, as you can see here, the crack velocity versus the applied stress intensity factor, you can see that hydrogen-assisted fracture is a little bit like fatigue. So you have a first stage where the crack speed grows very fast with applied load. And then you have a second stage where the crack speed is independent on applied load. And the reason is because it's diffusion limited. So the crack is growing in an intermittent manner, so it's jumping basically. And the time that it takes from one jump to the other is the time that it takes for the hydrogen atoms to go from the crack tip to this critical distance ahead of the crack tip where the cracking takes place. So if we look at experiments, we can figure out what is this critical distance, right? Because we know we have the crack, basically the crack velocity measurements is the ratio between the critical distance and the critical time. And then we also have 1D, the analytical solution for diffusion. So the distance that a hydrogen atom can travel is 2 times the square root of the diffusion coefficient of the material and the time. So we have a system of 2 equations and 2 unknowns, very simple. So we go to experiments. For example, this is an nickel superalloy, and we go to these 3 replicate points at the -1000 potential, and we get a crack speed of 4 to the -2 microns per second. We know the diffusion coefficient of the material, we substitute, and we get that the critical distance is 1 micron. So it changes, of course, from material to material, but we're talking about very few microns ahead of the crack tip. So if we had to choose a tool to tackle this problem, where we know that the micro scale is important, then normally we will go to discrete dislocations, but we are engineers, so we also want to be able to model big things. So we are stuck with continuum models. And we know that continuum models break down when you go into the micro scale. An alternative, what we could do is we could try to enrich our continuum models with the physics that is happening that we're missing, that you can capture with discrete models. And basically, the key thing that you're missing at those microns ahead of your crack tip at that micro scale is the effect of those plastic strain gradients that luckily for me, Lorenzo has already talked about it. So these are the classic torsion experiments of Fleck and co-workers. You can see under uniaxial tension, no gradients, no effect of no elevation and strength. However, the flow stress can be 3-4 times larger if you have an effect of the gradients in torsion. And I mean, there are many microscale experiments that show this behavior, as you know. So that's great, because that also means that, luckily for us, a lot of people have been working on developing theoretical frameworks to be able to capture this smaller is a stronger effect, this effect of plastic strain gradients of GMDs, this elevation of the strength. And you can see here that, for example, the predictions of one of these gradient models, and you can see that the agreement is very good. So we can quantitatively capture those predictions. So that's fantastic. And when many theories have been proposed, we decided to use the one of Gudmundsson, also Fleck and Willis. But most of these theories, what they have in common is that they're higher order theories. So you have some higher order stresses, work conjugate to gradients of plastic strain. And then you have the plastic work that depends not only on the plastic strain, but also the plastic strain gradient. And as a result of dimensional consistency, then you have a plastic length scale that comes into play. And by fitting that plastic length scale, then you can capture this. And this is important for us because in fracture, as it happens in microindentation, for example, is slightly different in that the sample doesn't need to be necessarily small, it can be very large. But what you have is a plastic zone that is physically small ahead of your crack tip, or ahead of your indenter. So what you see ahead of your crack tip or your indenter is that you have also these plastic strain gradients, these GFDs, and this is stress elevation. And in fact, if you plot the crack tip stresses ahead of your crack tip, you can see it here as computed by strain gradient plasticity and a conventional plasticity model like from Mises. You will see that far away they both agree, but as you approach the crack tip, there's some significant stress elevation. And this is important in our problem because, as I said before, our critical distance is of a few microns. So it's very important that we get the right stress level at the critical distance. But also because in hydrogen embrittlement, the hydrogen uptake and diffusion is very sensitive to the hydrostatic stress. So you really need to get your hydrostatic stresses right over that critical distance. So that takes me to the second ingredient. I'm going to explain how to couple that with the chemistry problem. So just to recap, we have solved two balance laws. So one is the balance of linear momentum, and then the other one is this microforce balance for the gradient plasticity. So now I'm modeling a third one, which is the hydrogen diffusion, which is an extended version of Fick's law, and it has multiple forms depending if you consider trapping or not. But the key point that I want to emphasize is that you can see here there's a dependency on the hydrostatic stress. So hydrogen accumulates in areas of high hydrostatic stress. In fact, if you plot this, if you show the steady state solution, it looks something like this. So you can see that the hydrostatic stress comes into play through an exponential term. So your hydrogen concentration is going to be very sensitive to your hydrostatic stress. It is very important that you characterize your hydrostatic stress properly. That's why we need the strain gradient plasticity in this case. And then also the same goes for the hydrogen uptake. That's, you have the chemical potential that is due to the environment. And as a result, you also have an exponential term with the dependency on the hydrostatic stress. So the solubility of the material changes with the hydrostatic stress. So again, very important to know your hydrostatic stress at the microscale. That's why these enriched continuum models become very important in this problem. Just to show some results, this is hydrogen concentration ahead of the crack tip. You can see for conventional plasticity and gradient plasticity, as you could anticipate from the previous equations, the amount of hydrogen that you have in the crack surface is much, much larger. And also close to the crack tip within the region of damage, the amount of hydrogen that you predict is much, much larger. So you need that enriched information, otherwise you're missing the effect that ENDs and dislocation hardening mechanisms have on this hydrogen concentration. And of course, it's very difficult to measure hydrogen over microns ahead of a crack, but there are some experiments that have been published. And as you can see, there's a bit of a scatter, but it seems that gradient plasticity predictions agree much better with experiments. In fact, there's two clear trends that we see with experiments that we cannot capture with conventional plasticity, which is that the hydrogen concentration increases as you approach the crack tip, and that the hydrogen concentration increases with applied load. So that takes me to the third ingredient of the model. We need to couple this deformation diffusion problem to fracture. For that, we use facial fracture because it's a quite compelling tool. And we heard yesterday about it, so I don't need to spend a lot of time on this. I'll just say that it's based on Griffith's energy balance. So cracking will take place whenever the energy stored in the material reaches a critical value. You can put this in a variational form as done by Frankfurt and Marigo, but then the challenge here lies on this term here because you don't know where your crack is. So then you adopt a regularization based on this phase field problem, where the phase field is kind of a marker that tells you where the crack is, and it's sort of a damage variable at the same time. So it goes from zero, no damage, to one fully cracked material, and then this surface integral becomes a volume integral, and you can solve this problem. And again, there's a length scale in there. It's sort of a non-local damage model. So there's a fracture length scale coming into play as well. Okay, so now the question is, we have the balance of linear momentum, the microforce balance, the hydrogen diffusion result, and another equation for the damage. The question is, how do you couple all of these ingredients? So we propose the first phase field formulation for hydrogen embrittlement, and then, well, I think it's straightforward to make this decision. So you say, what we see in the experiments is that the toughness decreases with the hydrogen concentration. So we can have this macroscopic observation. There's a function here that will degrade the toughness of the material. However, this is a quite universal choice, and that's, I guess, the beauty of the model. You can put in there whatever mechanistic interpretation you may have about this problem. You can make it a function of the dislocation density, of the hydrogen trapped dislocations, single boundaries, whatever you want to choose. But let me explain you our rationale. So I think the key point to answer is that how does hydrogen make metals brittle? So how can it be that a very ductile metal that fails by microvoid cracking suddenly exhibits some sort of intergranular fracture in the presence of hydrogen? You can see it here for nickel. And we have a hypothesis, and that hypothesis that the stresses are not high enough to reach the cleavage strength in the absence of hydrogen, and of course that's where we see ductile damage. But then whenever you have hydrogen, you lower your cleavage strength sufficiently such that if you account for this gradient and ridge stresses, these two lines cross and you get a shift from ductile to brittle damage. And again, I insist, you really need the gradients to get there. But let me elaborate a bit more. So this rationale comes from the following observations. First of all, when you do atomistic simulations, this is DFT for nickel, you can plot surface energy or fracture energy versus hydrogen coverage. And you can see that when you have quite a lot of hydrogen, so as you will see on this side, when you have quite a lot of hydrogen, you have a very significant reduction of the fracture energy by 40%. It goes down by 40%. So that's something that is very convenient because that means we can define our degradation law for the facial based on the atomistic calculation. So based purely on first principles. There's no fitting parameter whatsoever. So you have this, you assume a linear degradation, which is what you see in the DFT, and then you have this hydrogen damage coefficient that you can take here. This will be 0.41. So no fitting, you just take it from the DFT. If you believe the DFT, then you're fine. And then the next step comes from, okay, the challenge here is, okay, Emilio, but where are we in this graph? Because if you tell me that the hydrogen occupancy in this brittle interface, like a grain boundary, is very small, then, well, I mean, there must be another mechanism because you're not really reducing the fracture energy so much. And for that, we go into the thermodynamics and the kinetics of hydrogen diffusion and hydrogen trapping. And you can see here, this is taken from Oriani's equilibrium. So the yellow part, I'm plotting here hydrogen concentration versus binding energy. So how energetically favorable is for the hydrogen to go to grain boundaries, for example. And this is the trap occupancy. Yellow means full, blue means empty. And you can see that for grain boundaries, which is a binding energy of minus 40 kilojoules per mole, with very little hydrogen, less than 1 ppm, which is something that you typically get in your fracture process zone, your grain boundary is full. And you have an equation for that. So in your computational model, you can see as the hydrogen diffuses how your grain boundaries get full. And then with your grain boundary, you just go into this graph and quantify precisely how you lowered your fracture energy. And this is, by the way, what you see in the experiment. This is a recent science paper where what you see in red is the grain boundary, and you can see that all the hydrogen accumulates. This is with atom tomography. So we put this into a finite element model, and well, these are the residuals. As I said, we solve for 4 degrees of freedom. And let's see some results so I can show you that the model predicts what we expected. First of all, we do crack growth resistance curves. So this is on the vertical axis is the applied load. It's quantified by the stress intensity factor, and then on the x-axis is the crack extension. And the first result that you can see is that, of course, as you expected, as you increase the hydrogen content, you lower the fracture resistance of the solid. The second aspect is that we can capture the influence of the loading rate. So these are transient calculations, of course. So if you load very slowly, then your solid is going to be more brittle because there's going to be more hydrogen. Hydrogen has enough time to go to the fracture process zone. That's the main difference. And then we're going to check the influence of the plastic length scale. So the plastic length scale, I remind you, governs the capacity of the material to elevate stresses as a result of the GND density, right? So, or the plastic strain gradients. So what you can see here is that in agreement with expectations, if your material hardens a lot as a result of plastic strain gradients, then your crack tip stresses are higher and your fracture resistance is lower. But of course, this has to be normalized. Gradient effects depend on this non-dimensional set, so they will depend on the length scale divided by the plastic zone size, or in this case, R0 is a fracture process zone size, which depends on the fracture energy. So some materials you will be here, some other materials you will be there. And there's one extra length scale, which is the facial length scale. This fracture length scale that comes from the facial. And I just want to say that the facial length scale, if you solve the 1D homogeneous solution, you can relate the facial length scale to the strength. So by changing the length scale of the facial, you change the material strength. And then you see what you expect. As you increase the strength of your material, there's more plastic dissipation. So one thing that I'm going to do now, you can see here that when the R curve becomes flat, you get what we call the steady state fracture toughness. So I can change this length scale and I can compute this steady state fracture toughness. And this gives me the following figure. So brittle interfaces like grain boundaries or the theoretical lattice strength, we know that are on the order of 10 times the yield stress. So if these fracture lines cross this edge over here, then we have brittle fracture. Otherwise, we don't. And you can see here that depending on your choice of the length scale, you do or you don't. Of course, the length scale is a fixed material parameter. We know that it's on the order of 1 to 10 microns. So it basically depends on the fracture energy of the material that governs this R0. So let's say if you think about cleavage steels, ferritic steels, in low temperature where they exhibit cleavage, then you have an R node that is small, and you will be in this green line, and you will be predicting brittle fracture. However, usually in normal conditions, steels are ductile, metals are ductile, and you will normally be moving between 0.01 and 0.02. These are the normal values. So as you would expect, then the model, there's no hydrogen, this is an inert environment, the model predicts ductile damage. There's no, if you have a brittle interface with this strength, it will not be crossed. What happens when you put in the hydrogen? Well, when you put in the hydrogen, you see that those ductile steels that your model was predicting ductile damage, suddenly you have brittle fracture. So the model can capture this transition from ductile damage to brittle fracture without any fitting parameters, just considering this atomistic relation and just considering the kinetics of hydrogen embrittlement and the gradient plasticity. The gradient plasticity is key. Otherwise, as you know, in conventional plasticity, your stresses are too low. You're always too far away from this brittle interface. And just to finalize by showing some representative results, of course, the beauty of it is that by being an enriched continuum model, we can also model large-scale problems, so we can validate our model with experiments. This is, for example, showing the notch tensile strength versus the hydrogen content. This is for a pre-charged steel bars. These are double stainless steels subjected to a constant load. And again, the beauty of this is that we get good agreement with experiments, but we can also run experiments, virtual experiments over very large time scales, so we can decide which is this threshold for the strength of the material. We can also do virtual testing, so we can do virtual experiments like this one. So this is a standardized experiment to measure the hydrogen embrittlement resistance of screw anchors. You can see here we model a problem that involves contact. We have it also in 3D, so we can model in 3D. This is a contact between concrete and steel, and you can see how you can capture the failure of the bolt. And also, one of the advantages of phase field fracture is that it's very easy to introduce already existing damage, because you're solving for the damage variable, so to say. So you can prescribe the damage variable to be equal to 1 already in some areas. So then we can go and do what they call digital twins. So you go and couple your model with some non-destructive evaluation measurements. So you have this massive pipeline here. We model 3 meters of this pipeline, and you can see that the pipeline has a number of corrosion pits in there. So we can easily introduce those corrosion pits. As I said, we model 3 meters, and we introduce a few hundred defects in there. And we can introduce just by prescribing the phase field, so we don't need to do any complicated measurement. And then what we can do is we can load, let me see if I can show the video. Options to continue. How can I return? I just want to show the video. Well, it doesn't matter. Basically, what you see in the video is what you see there in those pictures. So we can prescribe the in-service loading conditions for the pipeline, and we can see how those defects start to grow, how those defects eventually coalesce, and how you get complete failure of the pipeline. And this is something that looks a little bit like a video game, but I should emphasize again that this is a quite sophisticated model, what is underlying, as I presented before. So that's all. I will just conclude by saying that I think that the strain gradient plasticity is a key element in developing predictive models for hydrogen embrittlement. 2 main reasons for this is that the critical distance is on the order of a few microns ahead of the crack tip, and that the material solubility, so hydrogen uptake, but also hydrogen diffusion, are very sensitive to crack tip stresses. So you really need to resolve that micro scale to get your critical variables right over your critical distance. And then what we saw as well is that the phase-in fracture method provides a very powerful platform for this coupled physical phenomena. So we can easily couple the formation, diffusion, and fracture. And we can do that in a mechanistic way. We can think of what's happening at atomistic scale. That's going to give us how the fracture energy degrades with hydrogen content. We can also introduce the hydrogen trapping kinetics to know exactly how much hydrogen we're going to have on those brittle interfaces. And if we couple all of this with the gradient plasticity, what we see is that we can capture this transition from ductile to brittle without any sort of ad hoc criteria. We don't need to have a trick in our model, a flag that tells us now you reach this critical concentration, you become brittle. Automatically, it's captured in a natural way by the model. It's a natural outcome of the simulation. And now I think we can also show that the model can reproduce laboratory experiments and deliver technologically relevant predictions at large scales. I would like to say before I finish that all the codes are openly shared on my website, so we have documentation and examples and so on. Feel free to download them and let me know if you have any issues. And of course, I would like to thank you and also the industrial partners and the research sponsors. Thank you. I forgot to say that I have a postdoc opening. If someone is, if you have very bright students about to finish, interested in getting some international experience in London, you're most welcome to apply. Thank you.